We have spent quite some time covering the modeling of a simple system fed with one substrate and degraded by one group of biomass. Treating real wastewater that has complex composition requires interdependent and interactive microbial communities. In this class, I will introduce the IWA activated sludge model that is used to simulate real-world systems. But first, let's quickly recap the simple model we learned. This diagram illustrates the energy flow and stoichiometry of biomass growth and decay. Recall that in the simple model, we used the conventional decay model for debris generation. In the conventional decay model, decay is regarded as a redox reaction with COD loss. From the stoichiometry and kinetic matrix, we can find the expression for reaction terms that can be used in the mass balances. From the mass balances, we can find the relationship between reactor performance, such as effluent substrate concentration or active biomass concentration, and operating conditions, such as SRT and HRT. When it comes to the application, the simple model has some limitations. It is restricted to soluble, readily biodegradable substrates. In reality, a large proportion of the substrates are slowly biodegradable compounds that cannot be directly utilized by microorganisms, but needs to be hydrolyzed by extracellular enzymes. They can be particulate, colloidal, or soluble. The simple model is a non-interactive model, meaning that there is assumed to be only one electron acceptor, typically oxygen. In real life, there are multiple electron acceptors and nutrients existing in the reactor, utilized by those interdependent and interactive microbial communities. Lastly, as I have covered in the last course, it is difficult to use simple model to describe multiple reactors in series, because it is difficult to unify the system-wide SRT and specific growth rate that are unique to each reactor. Here I introduced the IWA activated sludge model, or ASM. They are mathematical models used to describe multiple microbial activities potentially interacting with each other in bioreactors. ASM1 model was published in 1987 and includes basic heterotrophic organic carbon oxidation, nitrification, and denitrification. In the mid-90s, ASM2 and 2D started to include biophosphorus removal and the storage of polyphosphate in denitrifiers. In 1999, ASM3 was published with more realistic assumptions. As I mentioned that the simple model does not include degradation of slowly biodegradable compounds, ASM introduced XS, the slowly biodegradable substrates, SNS, soluble biodegradable organic nitrogen, and XNS, slowly biodegradable organic nitrogen. Please note that the slowly biodegradable compounds is not just particulate ones, but also includes soluble ones. They need to be hydrolyzed before being utilized for biomass growth. Including the hydrolysis process for the slowly biodegradable compounds made it possible to use the lysis regrowth model for the biomass decay process. Recall that in the lysis regrowth model, biomass lies to form debris and particulate substrates, which can be hydrolyzed to become substrate for biomass growth. There's no loss of COD during lysis and hydrolysis, as they are not considered as redox reactions. Here's an example characteristics table for an influent for ASM1 model. Note the highlighted slowly or particulated biodegradable compounds, and also note the presence of oxygen and nitrogen concentration. Despite being zero, the concentration of multiple electron acceptors along with other nutrients influence the biomass growth rate in the model. This makes ASM1 interactive. As a result, a system of mass balance equations is required to solve the concentrations of those complementary nutrients. But we can use the stoichiometry and kinetics matrix to summarize the process and their respective stoichiometric coefficients and reaction rates. Then we can use that to find out the reaction terms in each of the mass balances, such as substrate concentration, nutrient concentration, slowly biodegradable compounds concentration, and various biomass concentration in the reactor. Computer programs have been developed according to the mathematical model to help solve complex equation systems. But remember that the IWA model itself is a mathematical model. This is the ASM1 matrix. It contains processes like aerobic and anoxic growth of heterotrophs, biomass death and lysis, and hydrolysis of slowly biodegradable compounds and components involved in those processes, like various biomass and substrates. The process rate is determined by multiple complementary nutrients. The way to use this matrix is the same as the simple model matrix. Let's use the reaction rate for soluble substrate, S sub S, as an example. S sub S is involved in three processes: aerobic growth of heterotrophs, anoxic growth of heterotrophs, and hydrolysis of particulates. We can find the stoichiometric coefficient and the process rates. Note that the stoichiometric coefficient for S sub S for aerobic growth and anoxic growth are negative, as S sub S is consumed in those processes, but it's positive for hydrolysis as S sub S is generated during hydrolysis. We can multiply the stoichiometric coefficient by the corresponding process rates and add together the products for all processes in which S sub S is involved. This is the reaction term for S sub S in substrate mass balance. Correction factors eta are added to correct specific growth rates for different types of wastewater. There are several assumptions made for ASM1. The reactor operates at a constant temperature and neutral pH. Although the concentration may change, the composition of organic matter stays the same, so that the microbial community and the resulting stoichiometric and kinetic constants do not change. The correction factor, or the fudge factor, does not change with a given wastewater. The stoichiometric and kinetic coefficients for nitrification is not affected by other processes. There's no limitation of nutrients for microbial growth. The only limiting factors that controls the specific growth rates are the electron donors and electron acceptors. All particulate matter enters the reactor, starts being hydrolyzed instantaneously and homogeneously at an equal rate. The decay also happens at a constant rate independent from other factors. Lastly, the Garrett configuration is used for ASM1 but can easily be extrapolated to other configurations. Okay, let's look at some simulation results. Ekema and Murray initially used a simplified model that contains only soluble substrate, oxygen, and biomass to simulate the performance of a lab-scale reactor treating domestic wastewater with a varying flow rate. Although it captured the general trend of oxygen consumption rate over time, it was far from ideal. So they included the hydrolysis process for the slowly biodegradable matters. And then, the model predicted oxygen consumption rate matched the experimental values well. But the predicted MLSS was far lower than that's observed in experiment. It was likely because the decay process is not included, so the predicted MLSS only had active biomass. Once the decay process was included in the lysis regrowth model, the MLSS concentration could match. But the model underestimated the oxygen uptake rate. Perhaps there was nitrification occurred in the lab-scale reactor, which is not included in the model. So, the substrates and autotrophic biomass for the nitrification process was included. Now, both the oxygen uptake by heterotroph and the nitrifiers could be plotted out, and the total oxygen uptake rate matched the experimental values reasonably well. The predicted MLSS was also close to the observed one. Finally, I would like to deliver the 5 cautions by George Ekema about ASM1. This should also apply to all the following modern sophisticated models. Do not fall in love with your model. It is always an approximation of reality. Therefore, there are always compromises which results in limitations. We use the model to describe reality and should not adapt reality to your model. Again, there are always limitations in the model. Don't use it outside of their limits. Because we're working with complex mixed cultures, the kinetic and stoichiometric constants are the generalization of all microbial communities involved, which can vary drastically with feed characteristics. Calibration of those constants is sometimes required, but you need to understand these values and make sure that the calibrated values make physical sense. For example, you want to be cautious if you get a lower maximum specific growth rate for aerobic heterotrophs than anoxic ones or autotrophs, because it is thermodynamically unlikely. Lastly, you want to be clear about the goal of your model so that you can make the correct assumptions and compromises without sacrificing too much accuracy.